Last time we talked about count response models, and our trajectory is starting from Poisson regression. So that we have the count response yi, right? It follows a Poisson distribution, independently Poisson with its own mean mu I. And what does this imply? Poisson regression implies that the variance of yi must be equal to the mean of yi to be equal to mu I. But this is a quite strong requirement. What if the data doesn't satisfy this? So what if we have empirical evidence to say that variance of yi should be bigger than the mean of yi? And we call this phenomenon over dispersion. Okay, so to resolve this over dispersion issue, which will violate the Poisson assumption, we have two strategies. One is to do the so-called extra Poisson regression, in which we specifically specify the variance of yi to be just another parameter phi times mu I. If this phi is bigger than 1, it satisfies over dispersion. Okay, so we have this additional parameter phi. And what's interesting here is that we don't specify a new distribution. We're just modifying Poisson by changing the variance to be this one. And we're still using the exponential family formulation to start from there. So this extra Poisson, and some people call it quasi-Poisson, just to mean that it's not a real Poisson. It's kind of an idea that just borrow an existing distribution, modify it, instead of saying it's a new distribution, but we just try to adjust it somehow. So therefore, the application of extra Poisson should be the cases where the over dispersion is not severe. So it's still reasonable to assume it's Poisson, but with this adjustment, we can have a better variance estimate for the beta hat, for the coefficient. That's just it. Okay. And following this idea, quasi-Poisson, this approach, I just want to briefly mention that maybe we don't have time to talk about that in this class, but there's something you might want to learn about. It's something called very interesting called generalized estimation equation. Okay. So what this does is that it's a kind of approach, it's a general class of methods, optimization methods, just say. It's for parameter estimation and used in biostatistics. And these kind of methods were developed to account for dependencies among observations. So these were commonly used for like longitudinal data. What do it mean longitude? Sorry, longitude. Let me rewrite it. Longitudinal data. What it means is that it's a data type that's specific talk about patients. What you mean is that for each patient, you may have multiple measurements of the same patient along the time course. So at multiple time points, we measure the same patient. So therefore, it doesn't make sense to assume these data points to be independent, right? You must account for dependency. But that will make the, likelihood complicated to write. So therefore, generalized estimation equation can be considered as this can be considered as a relaxation. Let me see, a relaxation to mimic the score being zero equation. So what is the score? Again, we have this review again. What the score is, let's say if you have the likelihood, I'm just getting a deviation from this main topic, but just to give you another introduction to this big class of topic, big topic, which we will not likely cover. We will likely not cover. If they write the likelihood as L beta, then the log likelihood is just the log of a likelihood. We write a small L beta, right? So then the score is defined as this D beta, D L beta. So this is like the univariate version. Sorry, D beta. Oh, I'm sorry. Yeah, D L beta, D beta. Okay, that's the univariate version. But the scalar version of this is scalar version. The gradient, the vector version is this gradient. That's the score. And why do we need to set the score to 0? That's for MLE. So for MLE, if we want to find the beta hat as the argmax maximizer of L beta, if we want to do that, then essentially, if this log likelihood is convex, has one maximum, we can just we can solve it by setting the score function of beta, which is defined above, right? We set this to 0. This is what we do for MLE. And then what this generalized estimation equation does is to generalize this thing. So basically, it will construct something on the left-hand side to replace the score, as what we did with the quasi-likelihood. So we use the quasi-likelihood. You see the relationship is that quasi-likelihood versus log likelihood is what we do in this extra Poisson regression. Similarly, this generalized estimation equation, I'll just write GEE. This GEE would mimic this score function to 0 thing. So that's just the analogy. That's the relationship. So in other words, here, these modification ideas is not to change the distribution to another distribution explicitly, but we just change a middle step to something that satisfies better our purpose. And I think from this kind of ideas, you can also see why statistics, sometimes people call it an art, because there are a lot of the inventions, constructions for many reasons, including convenience. And for now, I think another very important factor to consider when we develop a new method is the scalability, like the large sample size, high dimensions, right? Can we make the method run? That's very important. Okay. That's extra Poisson. And the second one to fix this over-dispersion issue is negative binomial regression. Here, instead of just changing this log likelihood to quasi likelihood, what we do is we actually change the random structure. Here, we will assume that yi are independently following negative binomial distribution with mean mu(y) and dispersion parameter phi. So in this case, what we said last time is that the variance of yi will take the form as mu(i) plus mu(i) squared phi. This additional term, when phi is bigger than 0, you actually have over-dispersion. Okay, and for negative binomial regression, to estimate the parameter, the systematic structure stays the same. So for Poisson, extra Poisson, negative binomial regression, they all have the same systematic structure. So the systematic structure is always log mu(i) equals xi transpose beta plus, that's it, extra transpose beta. So note that in our discussion, there's no randomness in the systematic structure. Everything's fixed. And the reason is that we assume xi's, the covariance, to be fixed, and we assume the beta coefficients to be fixed. All right, so for the parameter estimation, what we said last time, for extra Poisson or quasi-Poisson, the estimation for beta hat is the same as in Poisson regression, using IRLS. It's just that the covariance matrix the beta have will be different. We have to factor in this phi, this value phi. For negative binomial regression, there are two ways to do it. If we fix this phi, we can still do IRLS to estimate beta. But if we want to estimate them jointly, we need to do MLE, maximum likelihood estimation, which cannot be reduced to IRLS in that case. Okay, so that's a review of what we did last time. Furthermore, besides over dispersion, there's another issue we should consider in reality. That is the count you get for yi. So you have y1 to yn as n observations. There might be too many zeros. If you have that issue, what would you do? So this is called the excess zero counts. This is another problem. How do we deal with this thing? With a high sparsity in our yi. This can happen in some data where you would likely have a lot of signals uncaptured. Okay, so for this, it's common in both social science and life science. So what we can say about when our data have excess zero counts, we can tell this by just count the number of zeros in our yi's. That is, we can compute the sum I from 1 to n, an indicator function that yi 0. We just count number of zeros. And we check this number versus if we assume the Poisson or negative binomial, we can get a probability of yi being 0 for each yi. So this is something we can get after model fitting. I just put a hat here to mean that it's based on our fitted model. Even our fitted Poisson model or negative binomial model, we can do this probability calculation. We can add it up. Then if this value seems to be much bigger than this value, then you have excess zero count issue. Then how do we do it? So if this is much bigger than that. There are two ways to think about it. One is that so basically what we need is to introduce yi's distribution as a zero-inflated version of the count distribution. So what distribution should it be? There are two types of models that account for zeros. One is called hurdle models. And this one was actually introduced, if I remember correctly, by a social political scientist, a quantitative political scientist, Professor Gary King at Harvard. So I think he was one of the very early people who used statistics in his research, and he basically introduced statistics to his field. And the hurdle model he proposed is like this. If we have, say, Poisson or negative binomial with 0, we can take values starting from 0, right? So for both Poisson and negative binomial, the smallest value you can take is 0, but we truncate that. We don't keep it. We only keep, let's say we call it 0 truncated Poisson or negative binomial. So for such distribution, the smallest count you can take is 1. You remove 0. And you re-normalize the probability so that these probabilities add up to 1. So you need to change the probability mass function. So basically, under this, let me just say it. The probability of such a yi, say taking a value c, okay? Let's just call it 0 truncated. Under the 0 truncated Poisson, I'll just say it. Under the 0 truncated Poisson distribution, this probability should be equal to the probability under just Poisson. Under the original Poisson, that yi equals c, divided by 1 minus the probability under Poisson that yi is being 0. So you're just dividing that by the non-zero part of the probability mass to re-normalize everything. So you need to change the probability mass function. With this, then hurdle model just add 0 to it. So what it does is that it introduced this new variable, which we use for mixture models as just an indicator. We introduce this zi indicator variable, which are IID Bernoulli pi, following a Bernoulli distribution with probability pi. Then what the hurdle model says is that you just consider the distribution of yi conditional on zi. What it assumes is that yi given zi being 0 would be a point mass as 0. Point mass being that the yi just take one value, 0, with probability 1. Okay, and the second case is what if zi is 1? Then such y will take the 0 truncated Poisson or negative binomial. The advantage of doing that is that you can change this probability value pi to introduce zero inflation, because this pi could be much bigger than the Poisson probability of y being 0. You can make it larger than that. Okay, so you see what this hurdle model means, or this kind of latent variable interpretation. It means, I think I can give you one example in a real life example. Okay, so for example, if I want to say, if I decide to go out for shopping, then the number of items I end up buying will be a Poisson count random variable. But whether I decide to go out or not is the crucial latent factor. Because if I don't go out, I will buy 0 for sure. If I go out, then I may end up buying 1 or 2. But there's another way to think about it. Because if I go out, I may still end up buying 0. So that depends on the personality. So that gives the second type of model, zero-inflated model, which means that we don't truncate Poisson or NB, negative binomial. We just keep Poisson negative binomial, and we add 0 to it. Yeah, so that's the second interpretation of it. The second formulation. So if I say, for this hurdle model, let's first wrap up this. If I just put it together as a mixture model, then what it is that yi is independently following pi with a probability mass of 0 plus 1 minus pi times a zero truncated ZT, zero truncated Poisson, for example, with mean μi. That's it. So you add a 0 component to make the 0 more. So one thing about the hurdle model, which I will not detail, is, let me see. Sorry, I should say that there's one thing that's very important to know about the zi, is that using this formulation, once you see yi, you know zi, because they have this one-to-one correspondence, right? Because when yi is positive, zi must be 1. When yi is negative, when yi is 0, zi is 0. So you have this one-to-one correspondence, which is good thing about this hurdle model regarding the interpretability, if we care about this latent variable for interpretation. Another thing is that because of this zero truncation, because of the need for renormalization, the likelihood is kind of complicated. You make the likelihood more complex. So that's why for parameter estimation under hurdle model, we mostly use methods of moments. I don't know how many of you have learned about that, but basically for methods of moments, it's a different way for estimating parameters. What you do is that you set the sample moment, like the average, to be equal to the expectation of the distribution. And then you set the second sample moment, which is the average of yi squared, to the expectation of the random variable squared. So depending on how many parameters you need, you will go down to how many moments. And then you solve the system of equations. That's what you do. So the good thing about method moment is that it's simple, usually fast. The bad thing is that such an estimator, method moment estimator, doesn't have nice theoretical properties as the MLE. So MLE became a dominant estimator. If you can do it, if you can have a likelihood and maximize it, it's good for several reasons. And the theoretical reason is the most important one, which is I think this has to be attributed to Fisher. Like he derived a nice theoretical property of MLE, including, if you remember the Kramer Rao lower bound, that thing, MLE can asymptotically achieve that bound as for its variance. And it's also asymptotically unbiased. So these are the nice properties for the MLE, as long as your likelihood is well behaved. Yeah. Anyways, this is the hurdle model. And then zero-inflated model, which I will quickly go over. Zero-inflated model is that you don't do the zero truncation. So you also have a Zi, but Yi and Yi given 0, 0 is also a point mass at 0. But Yi under Zi being 1 can still take 0 values. So this could be Poisson mu I or MB mu I phi. We just add this additional 0 component. So you see that for zero-inflated model, because you add, let's see, write it together. You add the 0 component in addition to the zeros already in your model. So in this case, you must have 0 inflation. So the 0 is getting more. One thing that's different about the hurdle model coming back is that if you set this pi to be less than this probability, you may end up having fewer zeros. So you can actually get fewer zeros, not just excess zeros, because all the zeros come from this point mass. It doesn't come from Poisson or negative binomial. So you can go down, not just going up. But for zero-inflated, you have to go up. This is similar to the difference between quasi-Poisson versus negative binomial. For quasi-Poisson, if you set this phi to be less than 1, you have under dispersion. But for negative binomial, you always have over dispersion. So there are many considerations for modeling choices. And also, I have to say that once you add more to your model, it will make the computation a bit more difficult. So something people criticize about the practicality of using zero-inflated, say, negative binomial, zero-inflated negative binomial regression practice is that the optimization for parameter estimation sometimes may not converge. Yeah, if you have that, then it's something you need to solve algorithmically, like how to, yeah. So optimization has become more and more of a real challenge for statistics because the model is just getting more complicated. All right, so do you have any questions so far before we continue? We basically finished GLM, the generalized linear model, finally. Yeah, we have covered the general GLM for exponential family with 2 specific examples, logistic or probit for binary response, Poisson negative binomial, and their variants for count data. That's it. And also one more thing I want to say is that you can even make this model more complicated by making this pi not common for all the observations, but make it specific to I. So what I mean is that if you go another layer of complication, you want to say that for different observations, the 0 degree of variation can be different, right? So you can have yi following pi I 0 and 1 minus pi I Poisson. So both pi and mu becomes I specific. But we cannot afford to estimate so many parameters. Then to make them less free, right? Less free, have to have fewer freedom. Instead of have pi 1 to pi and all free variable, we can link them together using another link function. So then if you do that, you need to have another systematic structure. Pi I here is 0 to 1 probability. So you will do logit pi I to be xi transpose. Now let's cut gamma. So it's just another set of coefficients we need to estimate to link covariates, use the covariates to determine the pattern. Yeah. But ultimately, all these models are assuming that there is some information that our covariates can tell us about the response, right? Including its mean parameter and its zero inflation. Yes.
I really was curious if there is if you just get data, how you're going to know which one to use.
I think that's why model selection is a central topic in statistical modeling. So the general idea is that we prefer a simpler model unless we have significant gain by moving to a complicated model. So that's why if the simple model is nested under the more complicated model, we use likelihood ratio test to compare the two models. Yeah. I'm sorry, could you say again?
I think that the five and that five.
That's a very good question. So the spike and snap prior is used in Bayesian statistics. The prior itself is a mixture, right? Yeah. So yeah, the same idea. It's like a mixture distribution. Yeah. Basically, when you use such distribution, you know that there's a point mass. That's something you cannot ignore. Yeah. And so it's an interesting thing that it's a mixture of a discrete point mass and the because here's discrete, but in that case, it's a discrete point mass and the continuous distribution mixture. Yeah. Yeah.
So what is the benefit of using the title output?
I think it's for interpretability. Yeah. So for the hurdle method, the benefit, well, I think two things. First of all, this pi can be less than this. So you can have like not excess zeros, but you can have fewer zeros. That's one flexibility. And the second thing is that it may give you better interpretability if you want to talk about ZI. What does this latent variable mean? Yeah. Yeah. So for example, maybe something I think I can give a better example is like, okay, if you take an exam, right? If ZI means if you take the exam or not. If you take it, your score won't be 0. But if you don't take it, then your score must be 0. Yeah. So it's just a different alternative. So that's why I think sometimes reasonable or models became popular by people who have domain expertise. Because with your domain expertise, you can have some intuition behind the model, right? To make it, to explain it. Yeah. Okay, so that's all for generalized linear model. Now let's talk about the final part of this class, linear mixed effect model or hierarchical linear model, which is the title of this class. But we have give you a lot of the foundation before we finally move there. So what does this title mean? Hierarchical linear model. It has different names, but they mean the same thing. So I just tell you that it's just the same as linear mixed effect model. It's just two ways to write the same model, whether as one layer or as a hierarchy. And this linear mixed effect model is often shortened as just linear mixed model. You will see these terms in literature. So therefore, for this one, many people write it in short as LMM, just like GLM for generalized linear model. Okay, so to motivate why we need this, we first introduce Bayesian linear model. We'll start from a Bayesian linear model. So in a Bayesian linear model, okay. So what we actually have is this. Let me just say that, okay, let me see whether it's better for me to write out this whole thing. All right. And if I have multiple, yes. Okay. So let's say that I have 38 schools, okay? And I have students from each school. So I will say NI students from school I. Okay, and I'm interested in the effect of the school on the students' some performance, academic performance. So maybe let's say that YIJ is the sum performance of student J in school I. Okay. And we have XI, so basically we don't need XIJ because we know that for the student, the school is I. We know that already. So in a linear model, we can write it just as linear model. We just have YIJ with some intercept, beta 0, and the effect of the school, okay? So we will have it just as the school, which is I, we have beta I plus epsilon ij. This is the model. We're assessing the effect of school I on the performance. We have one parameter per school, but for identifiability, we set beta 1 to 0 for identifiability. This is what we have seen before. It's just like here, the school is a categorical variable with 38 layers. So we have 37 parameters to encode the school. Okay, that's the model. And epsilon ij is just a random error. So how many parameters do we need to estimate in total if we don't consider the variance here? Because there's like a variance, let me just say x epsilon ij, if we just assume them to be IID, normal sigma square. There's a sigma square here. But excluding this, we have 38 parameters to estimate, right? One intercept and 37 offset, 37 differences. So for Bayesian, what we aim to do is that we assume these 37 coefficients are from another distribution. Okay, so the prior comes in that we assume, so I ignore beta 1, beta 2 to beta 38. They are IID from another distribution with mean 0, which means that I expect most of them to be not have to be 0. So the differences between these schools and this baseline is not big. And assume that there is some variation in their prior. So they could be positive, they could be negative, and this is specified by this variance tau square. So you see, if I change the model to this, how many parameters do I need to estimate? I don't need to estimate this 37 parameters anymore. I just need to estimate this tau square. That's it. So therefore, this Bayesian linear model essentially reduces the degrees of freedom in our model because we are estimating a hyperparameter instead of these parameters. All right, and what do we make sense of it? So if you're familiar with Bayesian, we know that the prior must have the so if a prior is a real prior, then the hyperparameters should be null, right? That's our knowledge. But in reality, in most applications of Bayesian, the hyperparameters are unknown. We just think, okay, maybe it's reasonable to assume these differences from beta 0, the school effects, to be Gaussian, because Gaussian is just convenient to work with. Maybe it's reasonable to assume Gaussian, but how big is tau square is unknown, right? So if we want to estimate, if estimating tau square from our data here are basically the YIJs. Then this is called empirical Bayes. you might have heard this term empirical space before. What it means is actually not as complicated as the name sound, I think. Basically, empirical base, it means that the hyperparameters in your prior are estimated from your data. Okay, so what do we do? To estimate the hyperparameters, including set like a tau square, we need a likelihood. Okay, so here, what we aim to write down are the parameters we need to estimate. So the parameters include beta 0, tau square, sigma square. So if we want to write down a likelihood of those three things to be estimated, essentially, it should be the joint distribution, right? That's how we define a likelihood. It should be the joint density function or joint probability mass function of all the data points. So I'll just write it abstractly as the density of data given the three parameters. Okay, but how do we get there? This is the density that combines two layers. One is this, one is this. So for the bottom layer here, the linear model part, if I write it in a distribution, it's actually, this is actually Yij independently following a normal distribution with mean as beta 0 plus beta I, variance sigma squared. This is the distribution we get in the bottom layer. And if we want to combine this distribution, this layer to this layer, so we just get a distribution of the Yij based on this and this. What is it? What is it, right? So we can write out this density by conditioning as a conditional density multiplied by a marginal density. So what we can do is that we can write the data as beta 0, beta 2 to beta 38. Okay, these betas and sigma squared. Okay, multiplying the density of those beta 2 to beta 38 given tau square. This is the second layer. This is like the layer about this prior. This is the data distribution, right? But once we multiply the two, these beta 2 to beta 38 will go before the conditioning, and they need to be integrated out. So what I'm saying here is that this is actually equal to the density of data and beta 2 to beta 38 given beta 0, sigma square, tau square. This is it. And to go from here to here, we need to take integration. So the integration needs to be taken both lines because they're equal. So once we take the integration, it should be over d beta 2 multiplied d beta 38. So with this integration, we can go to that. That's how we get to the likelihood of just the three parameters, beta, tau square, sigma square. And then we do MLE. Okay, so then you will get beta 0 hat, tau square hat, sigma square hat. These will just be the maximizer of this likelihood. That's it. And then with this tau square hat, we put it back in, and then we do Bayesian. So basically, for Bayesian, you want to get a posterior. The posterior would be the distribution of beta 2 to, I would just write beta I. Beta I given data is following what distribution, right? What distribution? It should be a normal distribution, but what should be its mean? What should be its variance? How are we going to update it from here? So that's the question to leave for your check. I can tell you the mean is still 0, but the variance needs to be updated by considering tau square from the prior and the variance from the layer of the data distribution. So that's the thing. But you can just imagine that tau square will be involved, and you're not going to use the tau square that's unknown, but you're going to use the tau hat square that's from the MLE. And this is what we call empirical Bayes. Okay, so this is the Bayesian linear model. And the reason I want to introduce this to motivate our linear mixed model or hierarchical linear model, this is already a hierarchy, you see, is that I want to tell you the practical reason why I want to do this. That is, we don't want to estimate so many parameters. That's the real reason. Otherwise, we wouldn't have good estimates for each one. For example, maybe you only have 2 students from one school. Then will you have a good estimate for that school's effect? No, right? But it's better that you pull the schools together and estimate this common variance. Okay, and then if you want to have an estimate from, maybe I should change this to 0. I think this is wrong. Yeah, there should be a question mark here as well. If you want to get an estimate for your beta I, then instead of using just a linear model to estimate beta I, we can use this posterior to give us a Bayesian estimate, right? So basically, if I call this A and B, then one possible estimator, a Bayesian estimate, I'll just write it here, Bayesian estimate of beta I can be written as beta I hat, which is just this A. So this posterior mean will naturally serve as a Bayesian estimate. Okay, and this posterior mean is a combination, will naturally combines the data and the prior. Okay, but the interesting thing here is that the prior parameters, hyperparameters, hyperparameter tau is also estimated from data. So in empirical Bayes, everything comes from data, except what? This prior shape. This normal distribution is what we assume. So this is additional assumption basically allows us to have fewer parameters to estimate. So therefore, I can use this example to give you a general principle in statistical modeling. That is, if you have few data, you need more assumption to do something, right? But if you have a lot of data, then you don't need so many assumptions. So this can also partly explain why no statistical model, I mean, I shouldn't say that, the probabilistic assumptions can be dropped in those machine learning methods, right? Because in that case, you're just more data driven. You have fewer assumptions about what's the truth. You just use the data to learn something in a brute force way. Yeah, so I think knowing this data sample size as your, how to say, budget, right? It's like a budget, and it's very important. So, and the model assumptions you have is about how, if you have very small budget, then you need to plan more, basically, or think more. Okay, so from now on, I will introduce the simplest, simplest linear mixed effect model. I think this is already it. This is like a linear mixed effect model with only the random effect. So here, let me just say that these beta 2 to beta 30A are called random effects. Okay, because they're random. They are effects of school, but they're random. Okay, so if we just go one more step, we want to say, what if the we have another covariate besides the school? Okay, so second example, let's just make it a little more complicated. We call this type of linear mixed model as random intercept model, which is the simplest, or I would say, which I wouldn't say simplest, but which is the most commonly used linear mixed model in practice. So still using the school example, besides the 38 schools, I am interested in one treatment, which means that we try to implement some education change in some schools, but not all of them. So if I have this additional thing, xi, which is binary, it means some treatment. And some schools are treated, others are not. Others not. So the schools naturally fall into two groups. And I want to assess the effect of schools. I want to assess the effect of this treatment like that. Okay, so in this case, you can see that this xi's effect is our major interest. But besides this xi's effect, we must consider that students from different schools may be different. So therefore, in the linear model, again, for yij, besides the common intercept, now we need to have an effect just for the treatment. And we call that xi is scalar, is indicator gamma. So gamma is the treatment effect. And we still have those beta I, right, to indicate the school-specific intercept plus epsilon ij. So compared to the previous model, the only thing we added is the xi gamma to indicate the treatment effect. Okay, so for this, I can tell you 3 types of models that we may use. So first one, let me just consider this, right? So the first model, I'll call it model A. So this model A means that we totally ignore school effects. And under this strong assumption, we set beta 2 to beta 38 to be all zeros. Okay, so they are ignored. Then in this case, the model is reduced to yij equals beta 0 plus xi gamma plus epsilon ij. Okay, what would be the effect? How do we get an estimate for the gamma? Actually, you can do it by linear regression, but we actually can come up with the same solution, same estimate for gamma using our intuition in a much simpler way. It's just that here the school doesn't have effect. Then we can just pull the students across the schools under treatment, and also we pull the students from the schools not treated. We take the difference of the 2 cohorts of students. That's it. Okay, so this gamma hat is just equal to the average of the yi's. I'll just simply say that average, instead of writing down the math formula, average of the yij for I being 1, for xi being 1, minus the average of yij for xi being 0. I just pull those students, compute the average, and the difference of the 2 averages is my gamma hat. Okay, but the problem here is that you totally ignore the school's effect. And it's possible that some schools are like the students in one school are more similar. And also it's possible that the school sizes are very different. So what if you have just a dominant school in one cohort treatment? Then you average them, you ignore that the students in one school are more similar. So you just have this average, the average you calculate here. And if you want to calculate the variance for the average, you basically you underestimate the variance. That's the problem. So the issue is always about this variance thing. So you need to talk about the variance of gamma hat. And when you do that, and you ignore the fact that the yij's have some dependency, right? You are trying to assume this model by treating all of them as independent. then your variance estimate will be problematic. It's like an underestimate of the true variance. And then you will have a problem. So basically, you are just overly confident about your estimate gamma hat, and then you may make, what's the consequence? The consequence is that you may think the gamma hat is big enough, so you believe gamma is non-zero. So you conclude, oh, there's a treatment effect. But this conclusion might be due to your underestimation of the variance of gamma hat. Does that make sense? Yeah. So that's why accounting for school structure is important, because students in one school may be more similar. And we will come back to this issue once we use the math to talk about it. You will see more clearly why there's like dependence induced by the schools. Okay, so that's model A. Model B. We just use this model, but we treat beta 2 to beta 38 as individual parameters to estimate. Okay, beta 2 to beta 38 are to be estimated. So there's no prior on them. They're just individual parameters. So in this case, we would have how many parameters? Beta 0, gamma, beta 2 to beta 38, and this variance sigma squared. So we have those ones. And so in this case, you would have this problem that for some schools, you might have too few students to estimate that beta I well, right? If school I has small ni, if school I has a small sample size, then this beta I hat has a large variance. It's just unstable. And model 3, model C is the empirical based one. Okay, so we just assume another layer, beta 2 to beta 38, as we did in the previous example. They are IID from a normal distribution with mean 0 tau square. So then you are still pulling schools to estimate this tau square. But compared to model B, your number of parameters is reduced from 37 to 1 here. And compared to model A, you still allow these beta 2 to beta 38 to be different. You didn't force them to be the same. So it's kind of in the middle. Okay, and that's the nature of empirical variance. It's a middle point between model A and model B. And this principle, so-called, so I have the relationship is model A is this here, most restrictive. Model C is on the other end, which is most free. And model B is in the middle, okay? It's in the middle thing. And this thing, model B drags model C towards model A. This type of idea in statistics is general. It's called the shrinkage principle, which is very general because I think you must have learned some penalization techniques like lasso or ridge for high-dimensional regression, linear regression, right? So they all have this Bayesian interpretation. So like lasso can be assumed to have a Laplace prior, and ridge can be assumed to have a normal or Gaussian prior. So these cannot be put under this empirical, actually, Bayes understanding, this Bayesian framework, let's just put it this way. And so what you're actually doing is that once you add a penalization, essentially you're shrinking coefficients towards the mean, right? And here we are shrinking these beta 2 to beta 38 also towards the mean through this prior, because this prior assumes that the Gaussian is very concentrated. It's very concentrated on its mean. We're assuming that these are not so far away from zero. So they, even though they can be different, but they cannot vary totally freely. Okay, so especially if you just go with model B, and you may have a beta I hat that has a large absolute value, and the possibility is that you just have so few data points, or 2 or 3 as your NI to estimate it. But if you are going down to model C, then such an estimate will be more if you go with posterior, because your data has such a small sample size, then the weight of your data will be smaller than the weight of your prior. So prior will play a bigger role to drag this estimate towards the 0. So then you will not have something very so-favored. So I think another way to consider Bayesian is that prior and data are kind of two things on your weight, and you are looking for a trade-off, and it depends on which one gives you more information. Yeah. So people who are like purely orthodoxical frequentists, they may not like Bayesian because of the subjectivity. They think the assumption of prior is too subjective. But I think this is something you know, it's something I would say philosophical about statistical inference, right? If your data is just so scarce, would you willing to assume more to make something out of it, or would you just say, okay, undecided, I don't conclude, right? That becomes a philosophical decision. But in this problem, which is more concrete, I think this Bayesian interpretation has this middle point thing, right? You're not going to model C because that's so unstable. You are not going down to model A because that seems to be too restrictive. So you're in the middle. But you can possibly change this Gaussian prior to something else, but Gaussian is just easy to work with. Okay. Any other questions? C and D, what? Oh, yes, yes. Thank you. Yeah, thank you for pointing out that. Yes, that's right. Sorry. Yeah. Yeah. Okay, so, oh, and also one more thing I forgot to say is the graphical interpretation of the 3 models. So if I have xi as the predictor, and I have my yij, or expectation of yij as my y-axis. Under model A, it's just one line, okay? There's only one relationship for all the schools. There's no, oh, maybe I should make it more clear. It's just 0, 1. So it's, yeah, between 2 points, there must be a line. So that's model A. For model B, you are just having one line per school. Okay, so this may be the line for school 1, this may be the line for school 2, and a line for school 38. You will have 38 lines, but they must all be parallel because they have the same slope for xi. Okay, the treatment effect is assumed to be the same for all the 38 schools. If you want to change that, then you will have a slope per school, and that becomes a random slope model. So that's a different model. Okay, model C is in the middle. So basically, we would have, okay, so basically we still have like an intercept or the common model for just school 1. And we're interested in other schools, how they change, right? So we would just basically compare to model B. We would drag all the 37 lines towards the line of school 1. So we have the shrinkage effect. They will all become more similar. So you end up having more similar lines. They're not the identical line as in model A, but they would not be as so separated as in model B. Okay. If your NIs are all big, if you have many, many students for each school, then the priors effect will diminish and the data will dominate. Then the differences between model B and model C will be small. Okay, so that's it. All right, any questions before we continue? It's because we set beta 1 to 0 for identifiability. That's the reason. Yeah. Yeah, the reason is we set beta 1 to 0. Yeah, but you made a very good point. I think your point is correct. The line, so okay, I think it's just difficult to draw, but this line from model A should be in the middle of the 38 lines in model B, right? And this, yeah, I should say that there is like the line, common line here, and this is a common line here, and they should all go to the common line. Yeah, thank you. I think that's correct. Yeah, but in that case, in this formulation, the common line should be the line of 1, just because of the identifiability assumption. Yeah. I hope that clarifies. Yeah, because I think the way I draw like order from bottom to up as 1, 2, 38, that's not reasonable. Yeah, it's just a very simple illustration. Okay, so now more generally, now let's be more notation. We talk about linear mixed model. We essentially have 2 types of covariates. That's why we have called mixed. 2 types of covariates. And we call them fixed covariates, or more exactly, I should say fixed effect covariates, because covariates are all assumed to be fixed in our setting. And we write them as in a design matrix. I just say a design matrix, or I just say xi, maybe I just say xi, it's p-dimensional. So if there's an intercept, we throw this into this p-dimensional fixed effect covariates. So what we assume is that their corresponding beta 1 to beta p are fixed. Okay, they are not random. So therefore, their contribution is xi transpose beta, and we have beta 1 to beta p fixed. We don't assume them to follow another distribution. They're just p parameters we need to estimate. We have random effect covariates. And we call them zi. And we assume them to be q-dimensional. So they have their own parameters. We write zi transpose beta, zi transpose gamma as the contribution to the response. And we assume gamma 1 to gamma q to be random. Okay, this is a general formulation of a linear mixed model. Back to our school example, the 38 slopes, beta 2 to beta 38 in that example are random, right? And what is the corresponding random effect covariate? It's the school indicator. It's the school indicator covariate. So we will encode every school to be a 37-dimensional 0-1 vector. If a student is in school 1, then the 37 dimensions will all be 0 because we leave out the first dimension, right? Just for identifiability. So school B to school 37, they're all 0. If the student is in school 2, then the first dimension for school 2 is 1, and the rest are zeros, right? If the student is in school 38, the last one is 1. So we have this 37-dimensional indicator. So in that example, Q is 37. Okay. In the previous example, we have P equals 2 and Q equals 37. And P equals 2 is that we have 1 for the intercept, we have 1 for the treatment effect diagram. Okay. Any questions? Okay, so then let's continue. All right, so as gamma 1 to gamma q follow some distribution, we could use what we write before, right? We just have their distribution written out. And let me see, maybe do I want to stick with this? In my previous notes, I used R, just for information. I used R, now I'm using Q. But I guess this is something we just have to be consistent. All right, so linear mixed model is mostly used when your data have clusters or groups. So that's why we use the school as an example. So here, every school is called one cluster or one group. And cluster, this name term cluster is often used in some clinical trials. We say patients belong to clusters, but don't confuse this cluster with the clustering in unsupervised learning. They mean different things. In unsupervised learning, the clusters are learned by unsupervised, right? In the unsupervised way, they're not predefined. They're learned by from data. But these clusters or groups are predefined. So when you collect data, you know which group they belong to. So maybe we'll just use group to avoid confusion. Okay, so for now, let's first talk about the data, the responses in group I. Say we have group I with Ni observations. So using the notations we have seen just now, we have yi as a vector. We put all the responses into a vector. It's yi1 to ni observations. And we have two sets of covariates. So the fixed effect covariates, we call that as a design matrix xi, and it's n by p, ni by p, okay? Ni by p dimensional. And if I write it out, it will be by row, I just write xi1, first observation in group I, to xip. Okay. And then I have random effects. Covariates. And I can write as zi, that's ni by q, okay? And I can still write it out by row to lay out the observations. Z I1 transpose to Z INI transpose. Sorry, I think I made a mistake here. It should be XINI instead of XIP. The P is the column. Okay. And correspondingly, I have my error. Error terms, I can call them epsilon I. I stack them as epsilon I1 to epsilon INI. Okay, putting it together, I would have the model for group I is yi is equal to xi beta plus zi gamma I plus epsilon. This is the model. Okay, now we want to understand it. So why do I say x and beta? Why does beta, because I'm just writing off of group I. Why doesn't beta have an why isn't beta I specific? The reason is that these fixed effect covariates are usually the things we are generally interested in their effects, like treatment effect, and we don't care the treatment effect being school specific, because when we, so for example, design a clinical trial, we think that we want the drug effect to be universal, and that's the universal quantity effect we're estimating. So it's not group specific. But this gamma I or zi gamma I still account for the differences in the groups, and then we let the coefficient to be group specific. Just like in our random intercept model, so the zi will indicate the schools and the gamma I will be the school effect. Okay, so in the random intercept model, right? In a random intercept model, in this context, or in this way to write it, I should say, Zi is just binary. It's no longer 37-dimensional because we're looking at group I alone, whether it belongs to group I or not, right? So then that's just the intercept. And then this epsilon I is the random error. Okay, so altogether, you see that beta as a fixed effect is the thing we want to estimate, we want to do inference for. Gamma I are not the things we want to infer. They are just the things we need to account for to make the model realistic. And we don't want to estimate them individually because otherwise there will be too many to estimate. But we need to account for them. That's why we group them together as a prior distribution. And we only need to estimate the prior parameter. Does that make sense? Yeah. Actually, I have to say, when I this is like many times I've taught this class for many times, but I have to say that when I first prepared this class, I feel like didn't find many good material about linear mixed model like online. Especially, I think a lot of books were practical, like they have R code, you can follow it to do it. But why do we do this, right? I think given the reason is the most difficult thing. Why do we want to do this model? There's so many models to choose from. Why this model, not the other model? And I found such consideration is most important when you do a model yourself instead of just applying a package. Because given that we have packages, it's your specification. What are the covariates you want to assume to be random effect versus physics effect, right? You need to justify your decision, right? So I think to me, the most reasonable thing to say is that these are the parameters that should be there, but they are not important. We don't want to do inference on them. Therefore, we just don't care about their individual values and put them into a prior. So therefore, we reduce the number of parameters we actually estimate. Okay. Okay, so that's all for today. And I think next Monday is a holiday, right? So I'll see you again on next Wednesday. Yeah, because we have some class cancellation this year. So we'll see. We'll see if we need, maybe we will have one lecture in week 10. Because originally we don't plan to do, but I think we can finish the rest of the material. And then we will have your final presentation, right? We'll have your final presentation and your papers. Yeah. Okay, so see you on next Wednesday.